Welcome back. In this session, we first see that in general, line integrals are depend on the path under consideration. But there are line integrals that are independent of the choice of path. For example, in gravitational and electric fields, the amount of work it takes to move a mass or a charge from one point to another depends only on the object's initial and final positions and not on the path taken in between. In this session, we also discuss the notion of path independence of work integrals and describe the remarkable properties of fields in which work integrals are path independent. We also describe the method of finding potential of conservative fields and discuss the test for exactness of differential forms. Line integrals of vector valued function over a smooth curve. We now review the definition of line integrals of vector valued functions over a smooth curve. If the smooth curve that C has a representation R of t is equal to x of t I plus y of t j plus z of t k, a less than or equal to t less than or equal to b, then the integral of f dot dr by ds along C from the fixed point A to the point B written as integral over a to b f dot dr by ds is equal to integral over a to b f dot dr, which is equal to integral over c f dot dr, is known as line integral of the vector valued function f along C. Two important questions that arise while calculating the line integral using integral over C f of r dot dr is equal to integral a to b f of r of t dot dr by dt. Equation number 1 are, first one, choice of representation. Does the value of a line integral in equation 1 with the given f and C depend on the particular choice of a representation r of t is equal to x of t I plus y of t j plus z of t k, a less than or equal to t less than or equal to b of C? The answer is no. 2. Choice of path. Does the value in equation 1 change if we integrate from the point A to the point B but along another path? The answer is yes. In general, this is illustrated in the following two examples. Example 1. If f is equal to 3x square plus 6yi minus 14yzj plus 20xz square k, evaluate where first one, C is a curve from 0, 0, 0 to 1, 1, 1 with parametric form x is equal to t, y is equal to t square, z is equal to t cube. Second one, C is the straight line joining 0, 0, 0 and 1, 1, 1. Solution. Here f is equal to 3x square plus 6yi minus 14yzj plus 20xz square k. Hence, we have the following. F dot dr is equal to 3x square plus 6yi minus 14yzj plus 20xz square k dot dxi plus dyj plus dzk, which is equal to 3x square plus 6y dx minus 14yz dy plus 20xz square dz. Equation number 2. 1. C is in the parametric form x is equal to t, y is equal to t square, z is equal to t cube at the point 0, 0, 0, t is equal to 0 and at 1, 1, 1, t is equal to 1. Substituting x is equal to t, y is equal to t square, z is equal to t cube in equation 2, we get the following. F dot dr is equal to 3t square plus 6t square dt minus 14t square t cube dt square plus 20t t cube whole square dt cube, which is equal to 3t square plus 6t square dt minus 14t raised to 5 2t dt plus 20t raised to 7 3t square dt, which is equal to 9t square minus 28t raised to 6 plus 60t raised to 9 dt. Moving from the point 0, 0, 0 to 1, 1, 1 means from t is equal to 0 to t is equal to 1. Therefore, we have the following. Integral over c f dot dr is equal to integral t is equal to 0 to 1 9 t square minus 28 t raised to 6 plus 60 t raised to 9 dt, which is equal to 3 t cube minus 4 t raised to 7 plus 6 t raised to 10 over the integral 0 to 1, which is equal to 5. Second one, the straight line joining 0, 0, 0 and 1, 1, 1 and is given in the parametric form by x is equal to t, y is equal to t, z is equal to t and t varies from 0 to 1. Substituting x is equal to t, y is equal to t, z is equal to t in equation 2, we get the following. F dot dr is equal to 3t square plus 6t dt minus 14t square dt plus 20t cube dt, which is equal to 6t minus 11t square plus 20t cube dt. In C, t varies from 0 to 1. Hence, we obtain the following. Integral over C f dot dr is equal to integral over t is equal to 0 to 1 6t minus 11t square plus 20t cube dt, which is equal to 3t square minus 11 by 3 t cube plus 5t raised to 4 over 0 to 1, which is equal to 13 by 3. Example 2. Evaluate the line integral with f of r is equal to 5zi plus xyj plus x square zk along the following two different paths with the same initial point a 0, 0, 0 and the same terminal point b 1, 1, 1. A. C1. The straight line segment R1t is equal to ti plus tj plus tk 0 less than or equal to t less than or equal to 1 and B. C2. The parabolic arc R2t is equal to ti plus tj plus t square k 0 less than or equal to t less than or equal to 1. Solution. A. By substituting R1 into f, we obtain f of R1t is equal to 5ti plus t square j plus t square k. We also need R1 dash is equal to I plus j plus k. Hence, the integral over C1 is obtained as follows. Integral over C1 f of r dot d r1 is equal to integral 0 to 1 f of r1t dot r1 dash t dt, which is equal to integral over 0 to 1 5ti plus t square j plus t cube k dot I plus j plus k dt, which is equal to integral 0 to 1 5t plus t square plus t cube dt, which is equal to 5 by 2 plus 1 by 3 plus 1 by 4, which is equal to 37 by 12. B. Similarly, by substituting R2 into f and calculating R2 dash, we obtain for the integral over the path C2 as follows. Integral over C2 f of r dot d R2 is equal to integral 0 to 1 f of R2 of t dot R2 dash t dt, which is equal to integral 0 to 1 5t square plus 2t raised to 5 dt, which is equal to 5 by 3 plus 1 by 3 plus 2 by 6, which is equal to 28 by 12. Remark. Results in the above two examples are different, although the endpoints are the same. This shows that the value of a line integral in equation 1 will in general depend not only on f and on the endpoints a and b of the path, but also on the path along which we integrate from a to b. Path independence of conservative fields. Now, our aim is to discuss the condition under which a line integral is independent of the choice of the path. We first consider some definitions. Let f be a field defined on an open region D in space, and suppose that for any 2 points A and B in D, the work integral B to A f dot dr done is moving from A to B is the same over all paths from A to B. Then the integral f dot dr is path independent in D and the field f is conservative on D. Definition. If f is a field defined on D and f is equal to del f for some scalar function f on D, then f is called a potential function for f. Theorem 1. The fundamental theorem of line integrals. Let f is equal to mi plus nj plus pk be a vector field whose components are continuous throughout an open connected region D in space. Then there exists a differentiable scalar valued function f such that f is equal to del f is equal to dou f by dou xi plus dou f by dou yj plus dou f by dou zk if and only if for all points a and b in D, the value of integral a to b f dot dr is independent of the path joining a to b in D. If the integral is independent of the path from a to b, its value is integral a to b f dot dr is equal to f of b minus f of a, equation number 3. Now, we only prove that f is equal to del f implies path independence of the integral and part 2 of the theorem. Suppose that a and b are 2 points in D and that C r of t is equal to g of t I plus h of t j plus k of t k, a less than or equal to t less than or equal to b is a smooth curve in D joining a and b. Along the curve, f is a differentiable function of t and we have the following. df by dt is equal to dou f by dou x into dx by dt plus dou f by dou y into dy by dt plus dou f by dou z into dz by dt using the chain rule, which is equal to del f dot dx by dt I plus dy by dt j plus dz by dt k, which is equal to del f dot dr by dt, which is equal to f dot dr by dt because f is equal to del f. Therefore, we have the following. Integral over c f dot dr is equal to integral t is equal to a to t is equal to b f dot dr by dt dt, which is equal to integral a to b df by dt dt, which is equal to f of g of t h of t k of t over a to b, which is equal to f of b minus f of a. Thus, the value of the work integral depends only on the value of f at a and b and not on the path in between. Example 3. Find the work done by the conservative field f is equal to x z I plus x z j plus x y k, which is equal to del x y z along any smooth curve C joining the points minus 1, 3, 9, 2, 1, 6, minus 4. Solution. With xyz is equal to xyz, we have the following. Integral over a to b f dot dr is equal to integral over a to b del f dot dr as f is equal to del f, which is equal to f of b minus f of a by part 2 of fundamental theorem, which is equal to xyz at 1, 6, minus 4 minus xyz at minus 1, 3, 9, which is equal to 1, 6, minus 4 minus minus 1, 3, 9, which is equal to minus 24 plus 27, which is equal to 3. Example 4. Evaluate the integral I is equal to integral over c 3x square dx plus 2yz dy plus y square dz from a 0, 1, 2 to b 1, minus 1, 7 by showing that f has a potential and applying equation 3 in theorem 1. Solution. Recall that the vector field f has a potential f if f is equal to grad f, that is if the following holds. F is equal to dou f by dou xi plus dou f by dou yj plus dou f by dou zk. That is, here if 3x square I plus 2yzj plus y square k is equal to dou f by dou xi plus dou f by dou yj plus dou f by dou zk. That is, if f of x is equal to f1 which is equal to 3x square, fy is equal to f2 which is equal to 2yz, fz is equal to f3 which is equal to y square. We show that we can satisfy these conditions. Integrating fx with respect to x, we obtain f is equal to integral 3x square dx plus g of yz, which is equal to x cube plus g of yz, where g of yz is an arbitrary function of y and z and not involving x. Now differentiating f with respect to y, we obtain f of y is equal to 0 plus gy. But it is given that fy is equal to 2y set. Hence, fy is equal to gy is equal to 2y set. Integrating gy with respect to y, we obtain g is equal to y square z plus h of z, where h is a function involving z alone. Differentiating with respect to z, we obtain the following: gz is equal to y square plus h dash of z, which is equal to y square. Hence, h dash of z is equal to 0. Hence, h is a constant, h is equal to 0 say. This gives g is equal to y square z, and hence f of x y z is equal to x cube plus y square z, and by 3 I is equal to f of 1 minus 1 7 minus f of 0 1 2, which is equal to 1 plus 7 minus 0 plus 2, which is equal to 6. Theorem 2. The following statements are equivalent. 1. Around every closed loop in D. 2. The field F is conservative on D. Proof. 1 implies 2. We want to show that for any 2 points A and B in D, the integral of f dot dr has the same value over any 2 paths C1 and C2 from A to B. We reverse the direction on C2 to make a path minus C2 from B to A. Figure 1. Together C1 and minus C2 make a closed loop C, and we have the following: integral over C1 f dot dr minus integral over C2 f dot dr is equal to integral over C1 f dot dr plus integral over minus C2 f dot dr, which is equal to integral over C f dot dr, which is equal to 0. Thus, the integrals over C1 and C2 give the same value. 2 implies 1. We want to show that the integral of f dot dr is 0 over any closed loop C. We pick 2 points A and B on C and use them to break C into 2 pieces. C1 from A and B followed by C2 from B back to A, figure 2. Then we have circulation f dot dr is equal to integral over C1 f dot dr plus integral over C2 f dot dr, which is equal to integral over C1 f dot dr minus integral over minus C2 f dot dr, which is equal to integral over A to B f dot dr minus integral over A to B f dot dr, which is equal to 0. Finding potentials for conservative fields. Now we give a test for being conservative. Theorem 3. The component test for conservative fields. Let f is equal to m of x y z I plus n of x y z j plus p of x y z k be a field whose component functions have continuous first partial derivatives. Then f is conservative if and only if dou p by dou y is equal to dou n by dou z, dou m by dou z is equal to dou p by dou x, and dou n by dou x is equal to dou m by dou y. Equation number 4. Proof. We show that equation 4 must hold if f is conservative. There is a potential function f such that f is equal to mi plus nj plus pk, which is equal to dou f by dou xi plus dou f by dou yj plus dou f by dou zk. Hence, we have the following: dou p by dou y is equal to dou by dou y of dou f by dou z, which is equal to dou square f by dou y dou z, which is equal to dou square f by dou z dou y. As continuity of first partial derivatives implies that the mixed partial derivatives are equal, which is equal to dou by dou z of dou f by dou y, which is equal to dou n by dou z. The other two equations in 4 are proved similarly. The second half of the proof, that equation 4 implies that f is conservative, is a consequence of Stokes' theorem and is omitted here. Example 5. Show that f is equal to e raised to x cos y plus yz I plus xz minus e raised to x sin y j plus xy plus z k is conservative, and find a potential function for it. Solution. We apply the test in equation 4 to m is equal to e raised to x cos y plus yz, n is equal to xz minus e raised to x sin y, p is equal to xy plus z. and calculate the following. Dou p by dou y is equal to x, which is equal to dou n by dou z. Dou m by dou z is equal to y, which is equal to dou p by dou x. Dou n by dou x is equal to minus e raised to x sin y plus z, which is equal to dou m by dou y. Together these equalities tell us that there is a function f with del f is equal to f. We find f by integrating the following equations. Dou f by dou x is equal to e raised to x cos y plus yz. Dou f by dou x is equal to xz minus e raised to x sin y. Dou f by dou x is equal to xy plus z, equation number 5. We integrate the first equation with respect to x holding y and z fixed and obtain the following. F of xyz is equal to e raised to x cos y plus xyz plus g of yz. We write the constant of integration as a function of y and z because its value may change if y and z change. We then calculate dou f by dou y from this equation and match it with the expression for dou f by dou y in equation 5. This gives the following. Minus e raised to x sin y plus xz plus dou g by dou y is equal to xz minus e raised to x sin y. Hence, dou g by dou y is equal to 0. Therefore, g is a function of z alone. And f of xyz is equal to e raised to x cos y plus xyz plus h of z. We now calculate dou f by dou z from this equation and match it to the formula for dou f by dou z in equation 5. This gives the following. xy plus dh by dz is equal to xy plus z or dh by dz is equal to z. Integration yields h of z is equal to z square by 2 plus c. Hence, we obtain the following. F of xyz is equal to e raised to x cos y plus xyz plus z square by 2 plus c. We have found infinitely many potential functions for f, one for each value of c. Example 6. Show that f is equal to 2x minus 3i minus zj plus cos zk is not conservative. Solution. We apply the component test in equation 4 and obtain the following. Dou p by dou y is equal to dou by dou y of cos z, which is equal to 0. Dou n by dou z is equal to dou by dou z of minus z, which is equal to minus 1. The two are unequals. So, f is not conservative. No further testing is required. Exact differential forms. Definition. The form m of xyz dx plus n of xyz dy plus p of xyz dz is called a differential form. A differential form is exact on a domain D in space if m dx plus n dy plus p dz is equal to dou f by dou x into dx plus dou f by dou y into dy plus dou f by dou z into dz, which is equal to df for some scalar function f throughout D. Notice that if m dx plus n dy plus p dz is equal to f on D, then f is equal to mi plus nj plus pk is the gradient field of f on D. Conversely, if f is equal to del f, then the form m dx plus n dy plus p dz is exact. The test for the forms being exact is therefore the same as the test for f's being conservative. The test for exactness of m dx plus n dy plus p dz. The differential form m dx plus n dy plus p dz is exact if and only if the following hold. Dou p by dou y is equal to dou n by dou z. Dou m by dou z is equal to dou p by dou x and dou n by dou x is equal to dou m by dou y, equation number 6. This is equivalent to saying that the field f is equal to mi plus nj plus pk is conservative. Example 7. Show that the differential form under the integral sign of I is equal to integral over c 2xy z square dx plus x square z square plus z cos yz dy plus 2x square yz plus y cos yz dz is exact, so that we have independence of path in any domain. and find the value of I from a 0, 0, 1 to b 1 pi by 4 2. Solution. Here m is equal to 2xy z square, n is equal to x square z square plus 2 cos yz, p is equal to 2x square yz plus y cos yz. Exactness follows from 6, which gives the following. Dou p by dou y is equal to 2x square z plus cos yz minus yz sin yz is equal to dou n by dou z. Dou m by dou z is equal to 4xyz, which is equal to dou p by dou x. Dou n by dou x is equal to 2xz square, which is equal to dou m by dou y. To find f, we integrate n and then differentiate to compare with m and p and obtain f is equal to integral n dy, which is equal to integral x square z square plus z cos yz dy, which is equal to x square z square y plus y sin yz plus g of xz. F x is equal to dou f by dou x is equal to 2x z square y plus gx, which is equal to m, which is equal to 2xy z square. Gx is equal to 0. Integrating with respect to x, g is equal to h of z, where h of z is a function of z along. Already g is equal to g of xz, hence y is not involved in the function g. Now fz is equal to 2x square zy plus y cos yz plus h dash, which is equal to p, which is equal to 2x square zy plus y cos yz, and hence h dash is equal to 0, so that h is a constant. Taking h is equal to 0, we have f of xyz is equal to x square yz square plus sin yz. From this and 3, we get the following. I is equal to f of 1 pi by 4 2 minus f of 0 0 1, which is equal to pi plus sin 1 by 2 pi minus 0, which is equal to pi plus 1. Example 8. Show that y dx plus x dy plus 4 dz is exact and evaluate the integral 1 1 1 to 2 3 minus 1 y dx plus x dy plus 4 dz over the line segment from 1 1 1 to 2 3 minus 1. Solution. We let m is equal to y, n is equal to x, p is equal to 4 and apply the test of equation 3 and obtain the following. Dou p by dou y is equal to 0, which is equal to dou n by dou z. Dou m by dou z is equal to 0, which is equal to dou p by dou x. Dou n by dou x is equal to 1, which is equal to dou m by dou y. These equalities tells us that y dx plus x dy plus 4 dz is exact. So, y dx plus x dy plus 4 dz is equal to df for some function f, and the integrals values is f of 2 3 minus 1 minus f of 1 1 1. We find f up to a constant by integrating the following equations. Dou f by dou x is equal to y, dou f by dou y is equal to x, dou f by dou z is equal to 4. Equation number 7. From the first equation, we get f of xyz is equal to xy plus g of yz. The second equation tells us that dou f by dou y is equal to x plus dou g by dou y, which is equal to x, or dou g by dou y is equal to 0. Hence, g is a function of z along, and f of xyz is equal to xy plus h of z. The third of equation 7 gives us dou f by dou z is equal to 0 plus dou h by dou z, which is equal to 4, or h of z is equal to 4z plus c. Therefore, f of xyz is equal to xy plus 4z plus c. The value of the integral is f of 2 3 minus 1 minus f of 1 1 1 is equal to 2 plus c minus 5 plus c, which is equal to minus 3. Now, it is time to summarize this session. In this session, we have first discussed that in general, line integrals are dependent on the path under consideration. We have also seen that there are vector functions called conservative fields for which line integrals are independent of the choice of the path. We have also described the method of finding potential of conservative fields and discussed the test for exactness of differential forms. Before going to the next session, let us try to answer these questions. If f is equal to 4xy minus 3x square z square I plus 2x square j minus 2x cube z k, prove that integral over c f dot dr is independent of the curve c joining two given points. Also show that there is a differentiable function phi such that f is equal to del phi and find it. Determine whether the force field F is equal to 2xz I plus x square minus yj plus 2z minus x square k is conservative or not conservative. Find a potential function f for the field f is equal to e raised to y plus 2z I plus xj plus 2xk. Evaluate integral over 1112 2 1 by y dx plus 1 by z minus x by y square dy minus y by z square dz. Here are some books for your reference. Murray R. Spiegel, Vector Analysis, Shom Publication Company, New York. N. Saran and S. N. Nigam, Introduction to Vector Analysis, Potishala Private Limit, Allahabad. Irvin Krasik, Advanced Engineering Mathematics, John Wiley and Sons, 1999. Shanti Narayan, A Textbook of Vector Calculus, S. Chand and Company, New Delhi. See you next time. Till then, goodbye.